Okay, thank you. Very nice. Thank you for inviting me. I'm glad that I could make it, despite various challenges trying to get here. I did manage to make it thanks to my many years of experience to come getting a visa and all these normal headaches. But here we go. I'm happy to share some of the questions we've been thinking about. And the context here is that transients, in order to be bright enough to see anything, are often coherent. Okay, these things often come together. So they are usually non-thermal, and just to distinguish, not just non-thermal, I mean synchrotron. You can have highly relativistic electrons that can emit perhaps all the way up to X-rays. But in those, I'm going to distinguish here, since different people mean different things from a coherence versus an incoherent process, that in a incoherent process, you have each electron doing something and radiating photons, and you add up the power of the energy of each photon. So if you have whatever 10 to the 30 photons, each one emitting some number of watts, you add up those watts. And that limits how much energy can come out, because your temperature has some finite Lorentz factor limit, usually not much larger than the rest mass of the electrons. So it's hard to get your temperature higher than a few MeV. And that limits the total energy output you're going to get out of the system. But in a coherent process, what you do is you have all the electrons move in the same direction at the same time. So you add electric fields. So you get a gain over an incoherent process by the square root of the number of electrons. So if you have 10 to the 30 electrons, you get a factor of 10 to the 15 boost in energy. So if we just compare, for example, the antenna, the thermal temperature of a TV transmitter, that itself is like a Planck temperature. These are enormous. So even in our own antenna systems, because all the electrons are pushed to go the same way at the same time, you can get huge effective temperatures and energies coming out. And these, of course, because they're coherent, they also can happen on arbitrarily short timescales and reach arbitrarily high intensities. And that's what we think allows us to see a large fraction of the class of transients, going from pulsars to nowadays we have white dwarfs and other objects that emit coherently. There are, of course, coherent processes even nearby, and the Earth has coherent decametric auroral emission. The emission processes, for theory, this is both terrible and perfect and excellent, that these processes are usually very difficult to compute, since you have to have electrons moving together, and there are many ways for them to do that, and usually you have some instability. The thing you can usually calculate is the linear part of an instability, but that's irrelevant. What matters is the saturation point of an instability, that's how much energy comes out, and that's almost impossible. So there are actually very few coherent processes for which we understand the physics. The history I've read about the Earth's decametric auroral emission. Okay, the Earth transmits at decameters from the magnetic poles, and that took them decades to agree that this is due to a tiny relativistic correction to cyclotron emission. So this is when you can fly airplanes and balloons and everything through and measure every electron. It took people decades to agree with both simulations, measurements, that this is what's going on in the Earth. If we look at other processes like pulsars, we refer to talks, and there I can assure you that people don't agree on what causes pulsar emission, because it is coherent. So even things for which is a huge amount of data, the number of pulsar pulses we have is enormous, and yet people don't agree. There's no shortage of ideas, but there's no consensus of what causes it. But anyways, this is, I'm going to talk about not what causes this emission, I don't know, but it does happen, but rather what can it be good for? And I'm going to present a consequence of these emissions, which is scintillation. So most sources in astronomical are, in some sense, thermally limited. If you want something to be bright, you both want a high temperature and a large area. That's how you get energy out. Just Stefan Boltzmann emission, right? You multiply sigma T to the fourth, and you just need a large cross section. So as an example, black holes. You've all seen the pictures of the Sagittarius star or M87 black holes. It's supposed to be the highest resolution object. In some sense, it's trying to hint at the smallest object out there at, say, 20 microarc seconds angular size. That's enormous. In FRB, the upper bound on this size is less than a microarc second. This is so much smaller than any black hole out there, any black hole emission, because black hole emission in the radio is incoherent. Generally thought to be incoherent. And it's consistent with being coherent because you have enough area. You have 20 microarc seconds. That's huge. Here you have probably more likely nanoarc seconds in emission. This is millions of times brighter than these black holes, and therefore tiny. And therefore these guys scintillate. So does that have a pointer? It does, good. So this is the first paper where we reported scintillation of an FRB. I just managed to persuade Leslie Sage that this is interesting enough. And you can see that this FRB gets brighter and fainter as you go up and as you go through different frequencies, just like pulsars. And that tells you that this is small. So black holes don't scintillate. Okay, so this is at least not this kind of scintillation, but it's often called diffractive scintillation. I think it's a terrible name, but that's what everybody calls this, meaning that you get tiny frequency scale structure. So in this case, the correlation function of the intensity varies of order over about a megahertz. Okay, you go from constructive to destructive interference. And that's what I'm going to use as our main feature of coherence. It's so bright that it's small enough that different lines of sight cause images that interfere with each other and cause this scintillation interference effect. Okay, no other source, certainly no incoherent source causes any scintillation in the ISM. And this is true. This is the only electromagnetic radiation for which it's true. For gravitational waves, it's almost always true because it's due to the brightness of emerging black hole. That's even higher. So that's a different story. But it was much harder to measure. There are many fewer black hole measurements than there are FRBs. So the signal to noise here is infinite compared to gravitational waves. So we should think of what to do with coherent effects. And actually, surprisingly, there are actually, I think, more papers on gravitational wave coherence interference effects than there are on electromagnetic ones, even though there's much less data. And people, I think of it as more clean. So let me go through and try to dispel some of the mystery of cleanliness. It's just the fact that you have interference means this is a precision measurement. Whenever you have interference, you know that you're measuring nanosecond timing delays between lines of sight. So you should think of what you can do with it. And can you see? I'm just saying things that everybody knows. Yes, there are many FRBs. And if you translate this number, okay, you're saying I'm measuring some delay to sub-nanosecond between lines of sight. After having propagated for gigaparsecs, so strain, the metric used of how precisely you're measuring a change of length, then these two lines of sight, you've measured to a strain of 10 to the minus 26. That's 1,000 times better than LIGO measures things at. This is by far the most precise measurement of something that's been measured. And you can think, so what are all the good things we can do with such a precise measurement that's better than anything anybody ever imagined or was ever achieved? It does have bizarre things. You might say, oh, why do we use this as a gravitational wave detector? It turns out this is actually, it would be a great gravitational wave detector for longitudinal gravitational waves. And this would far exceed LIGO. You wouldn't need LIGO, you would just use this if gravitational waves were longitudinal. Sadly, in fact, these give some of the best bounds on the scalar tensor limits, the scalar component of gravitational waves. And of course, it doesn't come as a surprise, never been detected. So there is no scalar contribution to gravitational waves, even at a part in 1,000 level. So unfortunately, not helpful. The transverseness means the distortion goes in the wrong way from the propagation direction, so you don't see an effect. Here I'm going to show you I think, an understood case of scintillation. This is to a pulsar. And this is a pulsar that I know many of you work on pulsars, maybe familiar object 0834 plus 06. It's good because somebody else took some data. Walter Briscoe and company took a VLBI data on it, so you can actually map on the sky what's going on and what's causing scintillation. So normally scintillation, as I showed, is similar to this FRB. As a function of frequency, you see this pulsar appearing brighter or fainter at different frequencies. For a pulsar, of course, you can keep observing it, and you can watch the scintillation pattern change with time. People have actually seen this for repeating FRBs as well. So a similar phenomenon has been seen for very active repeating FRBs. And then you see this crisscross pattern of scintillation. And for 50 years, after people have measured this, people had viewed this as being stochastic, as being just a random diffractive interference pattern. That's where the name diffractive came from, that this is a dense set of, it might as well be an infinite number of images in 2D that interfere with each other, and there's nothing, no useful information in there. It's just random. Now, down here is the same data, kindly, and they never published this, but they published this data that in the abstract sense that they had influences. But if you look at this is the intensity in a single dish. This is the visibility, okay, between in this case Arecibo and GBT. And in the visibility, so intensity is a real number. The visibility is a complex number of correlation between voltages. The intensity looks almost identical, because the real part of the visibility looks almost identical, just the total power. It's barely resolved, meaning they see almost the same electric field. The imaginary part of the visibility tells you the tiny differences between what the two antennas see. And this is a reasonably long baseline. It's, I don't know what it is, a few thousand kilometers from Arecibo to Greenbank. Now, what's striking is that you see, instead of having this crisscross pattern that's asymmetric and skew, in other words, this intensity is chi-squared distributed, these are actually randomly this is symmetric, equal amount of positive and negative features. You also notice that you have positive stripes, the red things run downwards, and the blue stripes run up. Okay, you look at it, it's obvious. And what it tells you is that, so the sign of the visibility tells you whether the light is coming from ahead of the baseline, on the one side of the baseline versus the other side. So the red point, if I get this right, the red point, again, the definition of the sign of the thing is not unique. Everybody has their own convention. But it tells you that objects on one side are moving towards you, whereas objects from the other side are moving away from you. So this can be due to the Earth moving, the pulsar moving, or the screen moving. But you see the relative motion of features to the left and to the right, which is why the blue and the red run in opposite directions. And because it's coherent, it tells you this is a very structured lens. And here's what it looks like on the sky. This data was taken by my friend and pioneer of this in this topic, J.P. Macquard. And if you now make an image with the VLBI data on the sky, this is what the pulsar looks like propagating through the interstellar medium. So it is, first of all, obviously one-dimensional. Okay, and that there were hints, Dan Steinbring and others were already understanding it from the secondary spectrum parabolic. But it's a very complicated story that I think very few people had the time to sit down and understand what it is, and I think most people were skeptical of what Dan was saying. But here's VLBI, much cleaner, and you can see you're done. Okay, it's just a straight line. The lensing caused by the interstellar plasma is an almost straight line with maybe some wiggles, but mostly straight. And then strangely, there's a cluster of points off to the side. This is what you observe. This is what interstellar plasma lensing does. First, a few good news. Being one-dimensional means you have a chance of figuring out what's going on, meaning you have more measurements. You measure a 2D dynamic spectrum and you only have 1D set of unknowns. Whereas before it was thought, oh, everything is 2D, it's just under constraint. And actually the opposite is true, it is over constraint. And you can actually map exactly what the flux out of every one of these images is going. And even these images turn out to be discrete. Okay, they start blending towards the center, but you can see they are individual images that are images of the pulsar that cause an interference pattern, and you can actually measure every one of them. Here is a analogous process. For any, I know some of you have been to Toronto. Next time you come, do enjoy, or I'm sure you can see this in India somewhere as well. Whenever you have a light source, this red, I think, is Scotiabank, and it reflects as a lake in front of Toronto, and there's an island that you can visit. You can take a picture like this. And you can see that if you see a reflection of a light, there's what's called a specular point. So that's a point on the lake where the angle of incidence is the angle of reflection, where if the lake were perfectly flat, you would have an exact image of that point in the lake. Now, of course, what you see instead is you see a large number of images that are blended in the middle, but toward the edge, you can see every wave leads to an image. Okay, that's what the image looks like. And far away, the number of waves that are steep enough to cause an image gets sparse. So you can see the individual speckles, the individual images. Okay, you can see that far away from the specular point, you get to resolve them. Nearby, they appear to blend if you have enough resolution, or if this thing was small enough, it would also resolve it. And here we go. And this is because it's grazing incidence. You say, oh, well, why is it stretched this way and not sideways? You can think about it. It's just geometry of reflection. So that's how you get 1D images. And this looks like very much like the image of the pulsar scattering in the ISM. So conclusion is, well, presumably the pulsar is passing through some inclined sheet with ripples on it. And if it's that simple, we can use, and of course we have quite a number of papers now on both measuring, modeling it, predicting it, that we can actually now use this scientifically to try to do some science and try to use this as our telescope. The interstellar telescope is baselines of billions of kilometers. This is a big telescope, much bigger than you can get on Earth. And you get resolution of picoarc seconds on the source. This is, you want resolution, this one circles around any resolution that you could imagine. This is picoarc seconds. So an example of how we can use this, I'm trying to use this to measure distances, for example. To measure a distance, you need an angle and a time delay. Just by triangulation, if you want to measure direct distance, right now there are people debate of the size of the universe, Hubble constants, dark energy, and there are disagreements about what's going on. You can ask, well, is there a more direct way of measuring a distance? And here, the simple way is lensing. In the past, it's been people have been trying this for 40 years now, of using time delay and gravitational lensing to get a distance. To get that down to 1% is difficult. You need to know the structure of the lens model. You don't actually know the exact distribution of matter, so it's been difficult to make this be the definitive measurement. Even though it's very clean. Okay, there's no assumptions needed. There's no distance ladder needed. You don't need Cepheids. You don't need supernovas. You only need things you think you understand. But of course, even there, you're limited by how well you know the potential. There's one potential you really know perfectly, which is the potential of a star. So for a point mass, it's just the Schwarzschild metric. So if you have a micro lens, then you know everything. There's no lens modeling uncertainties. There's only the mass of the object, a single parameter that you get to measure. You measure two images delayed by some time, and from the delay and the flux ratio, you know everything about the lens. Your lens is one number, you measure two. You're all set. Oh, there's one angle you need to measure. You need to measure the splitting angle, which is typically microarc seconds for micro lenses. So we're imagining a lens halfway between you and the source. That's where most lenses tend to be. FRB, a star somewhere in the universe, there are many of them. and you see, 1 in 1,000 FRBs will be lensed by a star. There are many thousands FRBs already measured, not published, but measured. So this may have happened already. And then, as I explained, the interstellar microlens allows you to actually resolve the angle. And from that, you can directly get a distance measurement across the universe. And the key here was that you had coherence. Two-screen lensing, it's a great topic for anyone interested. It's actually a lot of fun, a lot of interesting things you can measure. And actually, I think I'm running into the end of my time, so I'll just summarize that. There's fun things you can do about lenses, ask me on another day, is that we can now make very precise measurements using this coherence and interference of coherent sources. Thank you.
Any questions?
Thank you. Very interesting talk. I was just wondering, from the microsecond pulsar lens images, do you have a measurement for the radius of the pulsar?
Have I measured the radius of the pulsar?
Yes.
Okay, so the thing you measure is the separation between the emission points of different components of the pulse. So what you measure is that different parts. So this is we call them gates. So after 9 milliseconds, the pulse apparent position on the sky shifts by a few kilometers. Okay. Now, of course, the problem is that the pulsar radiation, as we don't know how it actually gets emitted or where it gets emitted from. And you measure the apparent sweep of the emission point, and because it's happening out in the magnetosphere, you can't translate this into. I can't say the pulsar is 15 kilometers across. That's may or may not be the case. Because you're measuring a point at some height, and the height is not known.
And finish.
Thank you, Professor.
Hi, Wesley. Can you hear me?
Yeah, please. Yeah.
Okay, thanks. Thanks, Wesley. It's always so interesting to hear about this conceptually interesting things from you. My question was probably like a more practical. For FRB side, to measure this kind of a delay, I mean, regardless of whether it is feasible or not, what is that we need to, or you are essentially advocating? Is it like measuring the same FRB on VLBI baselines and looking at comparing the visibilities, or is it like trying to look for like a copy of the FRB at some shifted by some certain delays in your very high time resolution data?
Yes, you're looking for an echo shifted by microseconds. Now, microseconds is short compared to the duration of most FRBs. So that's why you need coherence. So that's why you can't just say, I'll wait for an echo a microsecond later. That's hard to tell, unless you had a very short FRB. So the echo, you can see by looking at the voltage stream, right? You see a voltage coming down, and if it's coherent, then the next image over will have an echo of the voltage. And by shifting the voltage and comparing it, you can measure the delay. And in fact, if there are multiple images, you will just see a copy of the voltage for every image you have. And indeed, you need a VLBI array on Earth to know where on the sky is the image. So you need both a time delay and an angle. So yes, you do need a VLBI array on Earth, and then compare the voltage, the comparison of shifts between voltages at different stations on the Earth. So you need both, yes.
Okay, so in principle, if you have like a baseband recorder or transient buffer, the kind of things that is there, and say ASCAP or chime, this is in principle doable, right?
Exactly. So that's why I managed to persuade my chime colleagues to make the baseline continental, many thousands of kilometers, so you can actually resolve the screens and that you can actually do this. And people are saying, nobody cares about a milliarc-second localization since there's no other waveband at which you can do this. It's, why bother having a highly precise localization when there's no other waveband that you're going to do this at? And the reason is to do exactly this.
Thanks. Thanks, Will.
Thank you for the talk. I was wondering what is the chance probability of finding such micro lenses of FRB going through a star?
So the rule of thumb, for an object at a cosmological distance, I'm going to call that redshift of 1. Most FRBs are not quite that far, but roughly redshift of 1. The cross-section to being lensed by a population is roughly the omega in that population. Okay, the light is perturbed by the amount of stuff you have. Omega in stars, again, people, if anybody has a favorite number, I'd love to hear it. If you read through the books and the literature, it differs by a factor of 10 of how many stars there are in this universe. Sadly, even number of stars, I couldn't find, if you have a number, I'd love to know your number. But I'm going to pick a number of 1 in 1,000. Okay, omega star, I'm going to take 10 to the -3 as somewhere in the range, in the middle of the range that people discuss. Could be more, could be less, but yeah, let's say 1 in 1,000.
Hey, maybe.
Can you hear me now? Okay.
Yes.
Thanks. Very interesting idea with the using the scintillation to enhance the gravitational lensing. One potential complication I see there is that if you also have scintillation near the lens itself, so in the same galaxy where the lens is, that could mess up both the time delay between the images and the magnification, the relative magnification. So I was wondering if you've thought of that and what do you think are the best ways to get around it?
I mean, as you know very well, depending on where in the galaxy the lens is and how much delays it causes, I think for many FRBs, it's known to dominate the scattering, but in those guys would not be so well suited. But there's some that are minimally scattered as well. So there are certainly some, not all FRBs are going to be good for this purpose. Now, confusion is only moderately a problem because the VLBI will resolve our galactic scintillation. It will never resolve what's going on beyond the galaxy. So at least you will see on the sky which images are actually doing what you think they're doing. And then the other one is just a source of noise that one hopes you find an object for which this doesn't overwhelm you.
Okay, next question is from Visweshwar.
Yeah, my question was very similar to what Paz had. And when you have these signals, how are you going to separate the plasma lensing from the gravitational lensing? And I think that was the question which you just now answered. Yeah.
Again, VLBI. So the VLBI can resolve the plasma lens, but not the gravitational lens.
But that's also implicitly assuming that the screen closer to the source is not doing much.
Indeed, it could wipe out your signal if you're unlucky. Again, it depends on the regime you're in. So if the lens is really circum-FRB, as I think is my favorite interpretation, like the crab kind of case, that is in the immediate vicinity, it doesn't actually matter because none of these resolve it, and it just makes your pulse wider, but you don't care. So if it's close enough, you just don't care. But there could be an intermediate regime if the ISM in the host that, of course, is similar to our ISM. So it depends on the regime you're in.
Okay, great. Yeah, sure.
So if you have multiple points, multiple paths happening, then if you have multiple stations in the Earth, do you expect to see the same burst in different frequency range? Like, because you have a slightly different angle with respect to the screen, can addition of those points give rise to a potentially slightly different burst at different stations on the Earth?
Okay, I think you're asking whether this is separable. I've got a lot of things going on, and can I actually tell what is coming from where? Is this actually a tractable problem or not? So in the case of a pulsar, I think we know the answer. And it's pretty clean. We can measure the distance to every single scintillation. You can not only measure the angle, you can measure the distance. So, and it looks fully under control. And in the case of a pulsar, of course, it's highly overdetermined because we measure a two-dimensional function. And just empirically, our screen is one-dimensional. So we have many, many measurements for every point. In the case of an FRB, if it does not repeat, you have to ask, is it still overdetermined? And here, I think we're optimistic that the answer is yes, because it's not only one-dimensional, it's discrete. Okay, so that number of points is actually, and the number of lensing images is small compared to your bandwidth and your scintillation scale. So to us, it looks like, and the rest of the talk I didn't give about what I think is causing this, what's going on in the ISM is, I think we think these are what they call ducted alphanic waves. They're fairly generic. So we think we have a physical model of why it's happening.
Okay, I think it's a good time to end this talk. And thanks a lot, Wesley, for amazing talk. And let's thanks again. Yeah, thank you.